Network analysis. First, we'll look at descriptive and topological measures of a network. That is how we can characterize a network as a matrix or graph. You'll also want to use the Lecture 7 zip folder if you want to follow along with the practical examples within this particular module. So firstly, on a network of any kind, and a network here particularly we'll be talking about street networks being what you walk on or drive on outside. So these are streets. And Euclidean distance is obviously a very central component of network analysis, because it's through the distance, how long a street is, that we can determine how long in terms of time it would take, for example, to drive or walk down a particular road segment. And that's calculated just using Pythagorean's theorem. So there's nothing new here. We could also characterize a activity on a network, such as the mean journey length, for example. So that's one quantity that can be computed based on networks. So the mean journey length is simply for an agent being anything that traverses the network. We could figure out what the mean journey length would be, for example, for a delivery driver on a network. What is their average distance traveled over a number of days? And of course, we can have the standard deviation of journey lengths as well, which is the variability around the mean. And that can tell us, for example, for a delivery driver, how consistent their daily activities are within the network. Something with a large standard deviation would indicate that some days the driver drives very little, and some days the driver would drive a lot. And so the mean would not be as good of a summary for that particular driver, since it's very variable each day. Whereas a small standard deviation of the journey lengths would indicate that there's a very consistent amount of network traversed by that driver each day. And obviously that would be important in the context of all kinds of things that require driving on a network. Walking, you could also look at walkability. So for a particular agent, such as a person walking in a network environment, which we do every day, we could figure out the mean length of journeys they do each day and the standard deviation. And that can affect things like health outcomes for individuals, for example. The general idea then is one of path density. So path density being how much length there is per unit area. So it's simply the sum of distance over A. So how much path there is within a region. So A obviously means you have to do this within a region of some sort. And you would look at the total length of the network in there, divided by the area. For example, road density, drainage density, two common measures that are used frequently within the literature, derive from networks, particularly road density, for example, in the context of ecological analyses. We know where there's more road density, there's less diversity and sometimes species decline. For example, for amphibians as an example of that, because of roadkill, basically. Drainage density can help us understand how complex the drainage is within a particular geological or superficial geological unit. Now, in network analysis, we start with a real network, which is shown here in A, and we transform that into a graph representation in B. And in fact, B is transformed into another representation called the matrix. And it's this that's used in analysis. The graph representation is just a alternative means of visually understanding or looking at a network. So it gets rid of all the small, kinks that you see here, for example, in a network. Like there's a kink, and a kink is just where we have change of direction at a particular node in the network. And in a graph representation, that's removed. So this area here that had, these two kinks is removed with just put with a straight line. It shows what's important, which is the connectivity between this point and that point on the network. And these are junctions. Junctions are where we can have change in direction on the network. And they're represented by these junctions or nodes on a graph. So it's an alternative way of looking at a network, just to simplify it visually. And this is kind of what you see, for example, if you look at the OC transpo network. The OC transpo network, if you look at one of the bus maps, is a graph representation of the network. Well, it's a little bit more of a hybrid between the two, isn't it? But it's mainly a graph representation. It doesn't show the actual streets on a route map. It just shows the junctions and edges between them. Edges being these things, the lines connecting junctions. So junctions and edges are important concepts, as is the graph, as we'll see. So to the left here is a graph representation of connections in a particular network. A network, which is a small one for illustrative purposes here, that has 1, 2, 3, 4, 5 junctions. There are 5 junctions on this network, and 1, 2, 3, 4, 5, 6 edges. And this is a network which is connecting all junctions and all edges, which means that it is possible to traverse the network to get to any junction from any junction that you start at. If I start at E and I want to go to A, well, I go this way. If I start at B and I want to go to D, well, I just go that way. If I start at D and I want to go to A, well, there's all kinds of options. I could go that way and then that way. I could go that way, and then that way, and then that way. So there's all kinds of options, obviously, for traversal when you have a network in which all junctions are connected. And this might remind you of what we just looked at. We left off the previous module when we looked at cost distance analysis and stuff. We looked at the minimum spanning tree. And the minimum spanning tree is a graph theoretic and graph representation, analytic representation of a network. And in networks like this, these graph networks, we're usually interested only in the topological structure of the network. That is the connectivity between nodes by edges. Now, within a network, we can have what's called a minimally connected network. A minimally connected network would be, for example, a minimum spanning tree, like you saw in the previous module. So minimum spanning trees are a minimally connected network. It's one that connects all junctions by at least one edge. And so that means you can travel from the terminal junction or the origin junction to the terminal or origin junction, depending on what you want to call originating and terminal. So here, if we go alphabetically, A would be the source junction, and we'd have to go this way to get to E. Now, in a type of graph that we're showing here, which is called an undirected graph, so it's an undirected graph, travel between junctions is equal in both directions. So that means that the cost of traversing an edge from E to D is the same as going from D to E. Likewise for any other two nodes on that graph. So it's undirected in that case. That just means there's no direction to it. You can go in both directions and incur the same penalty or cost. That's different, for example, than in a real network, let's say like the road network in Ottawa. Once you impose things like one-way streets, well, that means you can only go in one direction from E to D, but you cannot go back in the same direction. That would be called a directed graph. So these are undirected graphs in this example here. Now, the minimally connected network, again, represented topologically, if you want the shortest or least cost path by the minimum spanning tree. The minimum will always be given by this, where the number of edges is equal to the sum of the vertices minus 1. Very easy to remember and easy to calculate. So all we need to know is the number of vertices to know how many edges would be in the solution, for example, for a minimum spanning tree. So if we have 1, 2, 3, 4, 5, right? 5 junctions, then the number of edges to minimally connect all those junctions would be 5 minus 1, or 4. And that's what we find here. We have 1, 2, 3, 4. So 4 edges are the requirement there. Now, knowing that there's 4 does not mean that a particular solution is the only possible one. Here, I'm just showing the alternate way of connecting all 4, which is from C, D, E, B to A. Instead of A, B, C, A, B, E. Also a possibility. So the number of minimal edges doesn't give us anything about the actual solution. All we know is that the solution should have 4. And you can think of in an algorithmic sense that if you're looking at a network and trying to find, let's say, the minimum spanning tree, you know that you should only look at solutions in which there are 4 edges. So you don't have to look at any other solutions other than when there's 4 edges to find out which of the ones with 4 edges is the minimum spanning tree, for example. So it's useful in that context. Obviously, this is also useful in understanding network complexity. Or general connectivity. Why? Because we can see how close, for example, a given network's graph is to one which would be minimally connected. Since minimally connected gives the minimum amount of connections, we can also then examine a actual graph for a particular network and see how different it might be from the minimally connected one. If it's much different from the minimally connected, that would tend to indicate to us we have more opportunities for travel and change of direction within the network. So it's more connected. And that leads obviously to what the maximal connections would be in a network. So we have minimal connections, then we have maximal. Now, this is maximal with what we call planar graph topology. Planar graph topology means that you can connect all junctions without ever having an edge cross another edge. So you'll see in this diagram here, for example, edges don't cross edges. The only time an edge is constructed is when it is going between two of the junctions and there are no crossing ones. There's a weird one out here going from A to D. And this is a universal connection here that's required for planar graph topology. So you can think of it as a edge in a higher dimension, in the next higher dimension, for example. Now, that particular solution here shows no crossing, so there's no crossing of the different edges. So we have nothing going, for example, from here to here, because that wouldn't be allowed in a planar graph topology. Planar graph topology means that all vertices have to be connected without intersecting edges. And the equation for the number or maximal number of edges is 3 times the sum of the vertices minus 6. So for this particular network, again, all you have to know is the number of vertices to get the theoretical maximum number of edges, or maximally connected network and the number of edges it should have. So if we have 5 vertices, we say 3 times 5, which is here, minus 2, because we factored out the 3. And we get 3 times 5 minus 2, which is 3. 3 times 3 is equal to 9. So with 9 edges, that's the most number of edges you can have in this network while maintaining planar graph topology. Now, real networks in the real world, the way they maintain planar graph topology, of course, is having overpasses and underpasses, right? So if you have another edge over here, for example, and you wanted to go from this edge right over to here to B, well, you would have to go over top of the other edges so they don't intersect. And so the drawing of that graph looks weird in 2 dimensions, and you end up with this type of an edge here that goes outside of everything. So we know the minimal and maximal number of connections then that are possible in any given network simply by knowing the number of vertices. The gamma index is used to compare networks among different locations, or just to understand how connected your particular network is by comparing the number of edges to the theoretical maximum number of edges, so that's Emax right here. We can figure out how connected our network is. If our network has the maximum number of connections, then gamma would equal 1, because the number of edges observed would be the same as the theoretical maximum number of edges right here. If, on the other hand, we have a network where we have no edges and just nodes, E would be 0. And so this would be 0, the whole thing. So gamma ranges between 0 to 1. 1 being a observed network which is maximally connected, 0 being a network that is unconnected. So for example, here we have 3 different networks. If we take this one, we can compute gamma, which is, we have 4 edges, so we'd have E equals 4 here, 4, and we have 1, 2, 3, 4, 5 junctions, so V equals 5. So 4 divided by 3 times 5 minus 2 is 4/9, or as a decimal, 0.444444, etc. So this network is slightly less than half connected. So it's not maximally connected, it's not even half the maximum number of connections, it's just slightly less than half. And so you could think of how this could be useful. Well, let's say you're comparing different delivery routes. So you have a fleet of cars or trucks that deliver, let's say, Amazon parcels. And you want to figure out which ones would be the most amenable to doing a second type of delivery or pickups during their routes. Well, routes that are more connected are easier to add things into, like picking up things, because they're more likely to go by or have access to many of the things in space. That could be pickups, let's say, and deliveries. So something that has a delivery that's near maximal connectedness has the opportunity to easily, along that network traversal that it does, to pick up parcels as well, because there's more opportunities for it to visit more places on the network. So it's one example. Or you could just be comparing different networks in different cities, different road networks. And the gamma index values could be plotted to figure out, okay, which ones have the best connections and which ones have the least. Then you can ask why that is and why that's important. We also have the number of circuits. Circuits are closed loops within the network. So for example, here that's a closed loop, closed loop, closed loop, closed loop. The number of circuits is given by the sum of the edges minus the sum of the vertices minus 1. So in this network example right here, we have, again, always 5 vertices, and we have 1, 2, 3, 4, 5, 6 edges. So 6 edges minus 5 minus 1 is 6 minus 4 equals 2. So there's 2 circuits in that network, and we can see where they are visually. But we could calculate that without having to visually look at the network. Why? Because most networks you can not just look at and see the circuits. These are very simple ones, right? Think of a network with 100 different junctions, or 1,000 junctions, or 10,000 junctions, and many, many edges in there. Well, you can't just look at it and say, well, these are the circuits. But you can compute them this way to tell you for a particular network how many circuits are possible. The maximum number of circuits for a given network is given by 2 times the sum of the vertices minus 5. So 2 times, again, we have 5 vertices, so 2 times 5 minus 5 is 10 minus 5, and that equals 5. So for this one right here, or any of these ones, the max circuits is the same. So 5 possible circuits. And there's a particular one that you don't see, which is this one up here, which is the fact that the start node has a circuit to itself, which you don't see. It's just part of the mathematics that has to work out. Just one that you don't see. So there's 5 possible circuits for that number of vertices. And generally that's going to be found in the maximally connected network. So an alpha index then allows us to compare the observed number of circuits to the maximum theoretical. And again, we have alpha ranging between what? Well, if we think of the observed number of circuits, the lowest possible is 0. Anything divided by 0 equals 0. So 0. And of course, in a planar graph topological network, this could be equal to the maximum. So that ratio would be 1. So again, this one ranges between 0 and 1. Where 1 would mean that we have the maximum number of circuits, and 0 would mean that we have no circuits in our network. So just edges, not edges I mean, but possibly just something like this, which is a plane graph. Well, not even that one actually, that would have 1, wouldn't it? Because we have 4 vertices. So if we have 4 vertices, we have 5 vertices, and 1, 2, 3, 4 edges. So we'd have 4 minus 5 minus 1, which is 4 minus 4 equals 0. So in a minimum spanning tree case, yes, we would have 0. So that's an example of a network with 0 circuits. And we can see that visually. And just working it out again for this one, we already know we observe 2, and there are 5 possible ones, and that gives us a 0.4. And that's almost like the gamma. Like the gamma index, right? It was also 0.444, but this is 0.4. So you can think of that as being, well, it has about slightly less than half the maximum number of circuits. And circuits are important because it tells you how you can get back to the place you started. And that could be important in a, let's say, again, I'll just use continue with a delivery context. If you have a delivery fleet working, you want to know how they can get back to the depot. So a network with more circuits in it gives more opportunities for the delivery people to get back to the depot and then start again on a new route, for example. So we look at some of those general means by which we can compare networks or utilize the information of a given network, its gamma or alpha indices, to figure certain things out. Now, networks generally aren't used like such, though this is just used as a graph representation, as a simplification for visual purposes. What's more important are the tables we can create off these, like what we call an adjacency matrix. The adjacency matrix contains all the information on the connectivity within this particular graph or network. So for example, we here see that A is connected to B by an edge. And so if we create a matrix where we have columns and rows labeled by the junctions, A, B, C, D, and E, A, B, C, D, and E, across the top, and the same for the rows. So we have column and row labels. So just the labels of the columns and rows of this matrix. The matrix is given by a bold-faced, or I should say just, not bold-faced, but the letter A. Here, capitalized. Then, A is connected to B. So we look across column A, like that, and then, I should say row A and column B. And where A and B intersect, right here, we put a 1. This means connected. A is not connected directly to anything else. So every other entry gets a 0. And I'll just remove that. So we found that A and B are connected, but A to A we don't consider self-connections. A is not connected to C, D, or E. So they gotta all get 0s. And then we go to B. B is connected to everything else. B to A, B to E, B to D, B to C. So everything gets a 1 there. B to A, B to B doesn't count, B to C, B to D, and B to E. Then we move on to C. C is connected to B and D. So in row C, B and D get a 1 because that means they're connected or adjacent to each other on the network. Everything else is 0. Then we look at D. D is connected to B, C, and E directly. So it's adjacent to them. So in D, B, C, and E get a 1. Everything else gets a 0. And then finally E. E is connected to B and D. B and D. Those get a 1. Everything else gets a 0. Now we have all of that information in this matrix. So all the information on what is connected to what is now in that matrix. And we could have a second matrix to go with that. let's say A, B, C, D, and E, and then A, B, C, D, and E. And likewise, we could then figure out, okay, well, A and B, let's say that has a weight associated with it, like a distance, that could be 25 units. So we could put between A and B 25, 0, 0, 0, and 0. Then for B, B to A is 25, B to A is 25, so that becomes a distance matrix, doesn't it? B to B is 0. B to C, that might be, let's say that's 10, so we put a 10 there. B to D could be 5. B to E could be 20. So we put that there like so. And we continue that, and then we could have both an adjacency matrix and a distance matrix. To capture the costs of traversing a particular edge. So it could be distance matrix, it could also be just time. So this could be in minutes instead of meters, for example. 25 meters, 25 minutes, whatever. We could have another matrix that goes with that adjacency matrix that summarizes all the information on the resistance or cost of going through each edge. We won't look at that one right now. It's not important at this point, but it's just to show you that's a second matrix that can be possible as a complement to the adjacency matrix. So the adjacency matrix is easy to understand. Wherever you see a 1, an A sub ij just means an entry with row I, column j. We have a 1 when two vertices are connected by an edge, and 0 if they're not. And so I don't even have to look at this anymore to know what's connected to what. I can ask questions just of this straight up matrix here. I can say, okay, for example, what D to A, are they connected? Well, I can look at either row D and column A right here, and it says no, they're not connected. I could have looked and said that, if I wanted to, at column D, row A. Same thing. This matrix, because it's created from an undirected graph, is symmetric. Let me spell that better. Symmetric. It's a symmetric matrix. And that simply means that along the diagonal, the upper, this is called the upper, and that's the lower. So the upper diagonal or lower diagonal are just mirrors of each other. So all the information that's actually needed is either in the upper or the lower. You can use either one. Generally, by convention, you use the lower. So you don't even need all this information in here. So all that can go. And everything you need to know about connectivity is actually just within this little lower diagonal portion right here. Because it's just the same information up here. So the properties then of that matrix are, we know that 1 means that two vertices are connected, 0 means they're not. The edges are undirected, and that's why the matrix is symmetric. It would not be symmetric in a directed graph, if it came from a directed graph. So it's not always the case that that matrix is symmetric. It has to have certain conditions for it to be symmetric, like we saw here. The other interesting thing is that we could, if it is a symmetric matrix, then the column sums, that's the sum of things in each column, let's say, 1, 2, 3, 4, 5, and 0 plus 0 plus 0 plus 0 is 0, right? So we have 0 plus 1 plus 0 plus 0 plus 0. And that would be equal to 1, right? Since zeros don't add anything to a sum. And B would be 4. 1, 2, 3, 4. C would be 2. D would be 1, 2, 3. And E would be 1, 2. Like that. So the column sums and the row sums would be the same, by the way. 1, 4, 2, 3, 2. Because it's a symmetric matrix. This tells us where the maximum column sum or row sum is. So this is our maximum is in B. So B has a column sum of 4 or a row sum of 4, depending on how you did it. And that maximum value tells us that B is the most connected. B is the most connected junction. Why is that important? Well, think of yourself as a retailer. As a retailer, and you're deciding where to put a new business, well, B, because it's the most connected, that node, having a business in the network near or at that node, would likely bring in more customers and be more successful than at, for example, A, which is only connected to one thing. Because you're going to have much more flow of agents through the network when you're at B. It's the most connected. If not there, then D will be the next one. And so this matrix, the adjacency matrix, has a lot of useful information about how things travel within the network. And so by itself is often, enough to answer many questions. Now, a given adjacency matrix raised to a power of n, this means A, for example, squared, which is matrix multiplication now, right? Columns times rows, A times A. So when we raise it to a power of 2, for example, then the number within that squared matrix, so the matrix squared, the number in there tells us how many ways, or I should say, the number of ways that we could move between the corresponding vertices in n steps, where n is the number within here. So let's look at an example. Here we have C and A right here. So C and A, or A and C. So A and C, that's the row. It has 0 here, 0 here, and then by the dot product in matrix multiplication, we get a 1 here. So that means to go between A and C, there is one way to move between those corresponding vertices. Or I should say there's 2 ways to go between A and C. So there's not 2 ways I should say, but 2 edge paths that would need to be traversed to go between A and C. Because this is based on the squared matrix here to the power of 2. And so when it's based on the squared one, this is the number of ways, the exponent is the number of ways to move between the corresponding vertices in n steps. So n is 2. So there are 2 steps to go. There's one way to go between A and C in 2 steps. That's the way to think about it there. So because there's a 1 here, there is one way to go between the corresponding vertices in exponent equals 2 steps. So A to C, and if we look at it ourselves, A to B to C is the only way to go in 2 steps. There's 2 edges, in other words, that have to be traversed. So steps mean edges. So steps equal edges here. Likewise, what about this way? What if we look at even the diagonal here? So that's B and B. How many ways to go between B and itself in 2 steps? Well, it's pretty easy. B to A and then back to B. That's 2 steps. B to C and then C back to B. 2 steps. To go to E, 2 steps. D, 2 steps. And we're done. So that's 1, 2, 3, 4 different ways to go from B back to itself. What about D to B? Well, D to B, there are 2 ways to go in 2 steps from D to B. And we can see that here. One way is to go from D to C to B, or from D to E to B. So there are 2 ways to go in 2 steps. Now, the diagonal of this squared matrix, when it's squared only, is the same as the column or row sums of a symmetric matrix. So we can sum them, or we can simply do the matrix times itself and take the diagonal, and that gives us the column or row sums. Another quick way to get that, which again tells us that B, so that's B and B over here, is the most connected because it has a sum of 4, is what we saw in the previous example when we looked at the properties of that matrix. Now, instead of recording the power of n, so that's the exponent value, at which the first, so if instead we record the power itself at which the element first becomes non-zero, then we have what's called the topological shortest path matrix. So that's a hard one to understand. So we go a to the power of 0. And again, this is our original matrix right here. So a to the power of 0 would give this. It gives us all ones along the diagonal, which simply says that in our matrix, we would record, this is the final, the D topological matrix. Because it was the power of 0, we would record 0 here, 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 and here. So there, 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 and there, okay? Because it's at the power of 0 that this matrix here has these values becoming non-zero for the first time. Then we raise our original matrix here again, a to the power of 1. So that's a to the power of 1. Now these ones become non-zero at a power of 1. So we would put a 1 here, a 1 here. And that, I'm not just copying the ones, I'm actually putting the power value up here. So this is the power value. And this is the cell value of the matrix to the power of 1, which is obviously just itself. But all those ones basically go as ones in here because they just coincidentally show up as ones in this case. Now to the power of 2, and we can see here, for example, which ones have stayed non-zero or which ones have stayed 0. Well, if you look at this one, and this one, just to focus a couple, those are still 0 at the power of 0, the power of 1. Then at the power of 2, those become 1s. So they will get a 2 up here because that's the power at which they became non-zero. So non-zero at this power for the first time. And at that point, there are no other values left in the original matrix that is down here at power 0 that are still 0. I should say that are in here that are still 0. So by the power of 2, for this particular graph, all of the adjacency matrix values have become non-zero. And so that's why in this here matrix called D topological, you only see 0, 1, and 2. Because remember, these ones became non-zero when the matrix was raised to the power of 0. They became all 1s for the first time because they're all 0s in here. And of course, because it's an adjacency matrix, to the power of itself, well, I should say the power of 1, not to itself, but to the power of 1, a to the power of 1. Well, these are just all the 1s here, so all those 1s just got put in there, because that was the power at which they become non-zero for the first time, which is, of course, when they're adjacent to each other. And then for these ones, all of the ones that were still 0, after the power of 1, not those ones there, that had not already become non-zero, which are these ones, they became non-zero at the power of 2. So 2 was put in here, 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 and there. So now we have what's called the topological matrix, or topological shortest path matrix. This is used, and it's important because it tells us that here, for example, to go between A and C, there are 2 edges that need to be transversed along the topologically shortest path. And of course, A to C would be A, B to C. So 2 edges. And the maximum value in here, of course, tells us the is 2. So we can say that we can find the shortest path, or any shortest path that is found between any nodes, any 2 nodes in this particular graph, is going to have 2 edges being within it. And that again helps to limit the alternatives that some algorithm might put forth, let's say, and you're searching through them, you know that the shortest path between any 2 nodes will have at most 2 edges to be traversed. It doesn't tell us which edges they are, but it tells us how many there will be in the shortest possible path to go between any 2 edges.